Thank you, Sasha, and the rest of the organizers for inviting me. Your series seems very successful and long running, which I applaud you for. I'm going to talk to you today about the active origin of the Northwestern Basin and Range. So we're really not going to be talking about the core of the Basin Range. We're going to talk about the very corner of it. And it's an interesting part of the North American origin, in so much as Western North America, as is shown in this map, is a broadly deforming region for geographic location. This is the Canadian border up here, and the Mexican border is down here. And as is well known, the modern origin is overwhelmingly dominated by shear in the south across the San Andreas Fault. This is a map of surface velocity, primarily coming from geodetic data, which shows the San Andreas Fault having a strong component of right lateral shear, but that deformation extends from the San Andreas Fault into the North American Cordillera, which is a different origin, an older origin related to Andean style shortening. As you go to the north in Western North America, you can see that the Basin and Range, which is this region down here, extends across into the northern part of the U.S., but that the plate boundary fundamentally changes from a shear boundary to a subduction boundary. North of this point, the Mendocino Triple Junction, there is a small oceanic plate, the Juan de Fuca plate, which is subducting underneath Western North America, and thus the evolution of Western North America is fundamentally linked to propagation of a triple junction over the last 30 million years and the response of the North American plate to that forcing. When you're in the north, in the subduction boundary, we have a very typical ocean continent subduction system in which the Juan de Fuca plate is diving underneath North America, generating a series of arc volcanoes, the Cascade Arc. And the largest seismic hazard in our region is by far and away the Cascadia subduction zone, which generates great earthquakes as large as magnitude 9, some people think. If you look at the velocity field in Western North America, however, and strip away the effects of the locking on the Cascadia subduction zone, excuse me, what you see is a vertical axis rotation field. Now, I just have to keep remembering to orient people here. This is the coastline here. This is Vancouver Island up in the north. I assume people are seeing my pointer. If not, somebody should scream or do something that is appropriate for Zoom. And then there's an important state boundary between the state of Oregon, which is in the south, and the state of Washington in the north, which is demarked by the Columbia River, which is the place in which the famous Missoula floods, the glacial outburst floods, came down in the late Pleistocene. But the point of this slide is to illustrate that if you look at the velocity field as denoted by geodetic measurements, what you see is a strongly rotational, vertical axis rotational velocity field about a pole somewhere near the border between Oregon, Washington, and the state of Idaho, which is right off to the right-hand side here. What that means for the kinematics of the northern part of the Basin Range, which is down here as illustrated by the classical Basin Range topography, is that there is a change in the style of deformation as you go from the south, where crustal velocities within the North American plate are moving north and west to the middle part of this arc, where velocities are moving largely to the north. And then finally, when you cross into the state of Washington, the velocity of points on the surface are moving to the north and the east. And thus the kinematics of the Basin and Range and the termination of the Basin Range is fundamentally linked to moving along this arc from northwesterly to north to northeasterly velocities. The bedrock underneath this velocity field is strongly dominated by a large four-arc crustal block that's often referred to as Celezia, which on the left-hand side of the figure is illustrated by this magnetic anomaly map. Celezia is about a 50 million year old, approximately over-thickened piece of oceanic lithosphere. Over-thickened in so much as in the state of Oregon, the block is as much as 30 to 35 kilometers thick, but by the time you reach the Olympic Mountains right up here, Seattle, Washington is about right here, or southern Vancouver Island, that same block is only 7 kilometers thick and has normal oceanic crustal thicknesses. And working out how this transition out of the Basin Range happens is complicated by the fact that the Celezia block is overlain by arc volcanism that ensued following the suturing of the Celez block to Western North America, and includes 2 belts of volcanic rocks, the older so-called Western Cascades and the modern arc, which is known as the High Cascades. And I'm going to talk about this region right here where the arc, the Basin Range, and the velocity field all impinge upon one another. So the current paradigm for how North American orogenic deformation works in the North American plate of Cascadia looks something like this. And this is a representation of a model by Ray Wells of the US Geological Survey from the late 1990s, in which the Celezia block, or the Oregon Coast block, it has many names, is moving in the south northwest, in the north more northerly, and by the time you reach Washington is moving northeasterly. And as a result of that, the back arc, or the region of the Basin Range, changes from a region of crustal extension in the light blue here to a region of crustal shortening. And what I'm going to focus on today is this region in the box where this transition between transtension and really oblique shear occurs at the very northwestern corner of the Basin Range. And for those of you who know anything about some of the detailed geography of this region, Portland, Oregon is right up over here. This is the Columbia River coming through here, and Bend, Oregon, which is a growing Eastern Oregon community, is denoted by this B. So my goal here is to talk to you about the geology in 3 boxes as we go from the south to the north, from the region where the Basin Range is very clearly developed to where it turns into a broad shear margin in the north, and describes some of the characteristics of the faulting and the timing and rates of deformation. I should say, I've got to back up, I apologize for this. That means that from the point of view of the provinces of Western North America, we're going to start in what's known as the Walker Lane Belt, which is a belt of transtensional shear on the east side of the Sierra Nevada, which extends up into the Cascade Arc in Southern Oregon, the Basin Range, and then into this sort of neutral area where you're not in any specific known tectonic province. Okay, so I'm going to start here in the south, and the main point that I'm going to try to make is illustrated well on this map of fault density. So this is just simply a running window measuring the number of faults per some unit area through this map of faulting. And what you see is that the zone of the most dense faulting is actually lying well to the east of the Cascade Arc, which is indicated by this white area of high topography. And some of the volcanoes may be known to you, like, for example, the Crater Lake volcano had a famous eruption about 7,000 years ago. All right, so what we're doing is looking along a boundary across which oblique shear is separating the Oregon coast block from the back arc, and is in part where the northwestern end of the Basin Range is located. So in the Klamath Basin, what you see is very clear strain partitioning, and it's illustrated on earthquake timescales as well as geological timescales. 2 damaging earthquakes in Southern Oregon in 1993 had very clear normal faulting mechanisms at a depth of about 9 kilometers, and it's thought to have ruptured this red fault system on the left-hand side. That bounding range. Here is the basin, the Klamath Basin, and the important part of this earthquake for me is an aftershock sequence which showed clear strike-slip fault focal mechanisms that broadly correlate with this fault zone here. And so what I'm going to show you is the geology of 2 places. One is this southern box, which shows geological evidence for right lateral slip, and this box up here that shows good geological evidence for normal slip. Okay, this is a LiDAR image and a geological map down below. You can see a glacial moraine here with a fan delta complex, which is broadly coeval with it, and in a series of faults that of streams that cross this fault system. You can see most clearly here in site B a right lateral offset of a fan, which is probably in the neighborhood of about 20,000 years old. And that right lateral offset is about 6 times the vertical offset at the same site. As you go farther to the north, you can see a series of moraines of the same age. You can see a moraine crest here and another moraine crest up here, and a very clear scarp on a north trending fault, which offsets the crest of that moraine. It offsets the crest, another fault in this fault system offsets the crest of this moraine. This Wobbin profile is through a late Pleistocene last glacial maximum moraine, and this is through a probably stage 5 advance during the interglacial. And what these show is about 1 to 2 meters of offset since 20,000 years ago, with about 20 meters of offset since about 100,000 years ago. And so by Oregon standards, these are actually very high slip rate faults in the tenths of a millimeter per year.
Andrew, you're at 10 minutes now.
Okay, I think I'm doing okay. So as you go into the north out of the Klamath Basin, those north trending faults I just showed you are shown here in this image. There's a strong step to the right into a northeast trending fault system called the Walker Rim Fault, and I'm going to show you that. Then a fault within this graben, the Lapine Graben, and then end up here at the Sisters Fault Zone. And the point of this map is to, first of all, navigate you through the talk, but also to show you that there's a very large quaternary graben here. These are contours in meters, which show there's 400 meters of quaternary sediment in the corner where the Walker Rim Fault system intersects the Sisters Fault Zone. And at that same corner is located a very large basaltic shield volcano, the Newberry volcano. So this active faulting is both localizing sedimentation as well as volcanism at the intersection between these two fault zones. The Walker Rim Fault Zone has a very clear topographic escarpment. It's a very typical Basin Range-like fault in Oregon, in which there's hardly any tilt, but the fairly large vertical component of deformation. The vertical component here is about 300, is the topographic relief, which is a little over 300 meters. And the oldest unit offset in the hanging wall, or the youngest unit offset in the hanging wall, is a 4.4 million year old basalt. So here's a normal fault that has a very low slip rate of about 1/100th of a millimeter per year. As you go north into the Lapine Basin, this north trending fault is illustrative of how oblique slip is occurring. If you look at the LiDAR image here, you can see a riser for a fluvial terrace that has a right lateral offset and a vertical component of slip. So if you focus on the geological map over here, and we can just pick one of these profiles like profile E, you can see about 1.6 meters of vertical to almost 7 meters of lateral displacement on the Lapine Basin fault. And this is also late Pleistocene in age. As you go farther to the north, here's the flank of Newberry caldera, and those little pock marks are monogenetic eruptive centers. And emerge from underneath the flank of Newberry, you find a distributed fault system, which is known as the Sisters Fault Zone, and it extends from the Newberry volcano into the Cascade Arc. These are arc volcanoes all the way along here. The northernmost one in this image is Mount Jefferson right here. This is an active structure. It offsets flows of various ages. On the flank of Newberry, it cuts Holocene flows that erupted from fissures along the fault system. In these images, I'm showing you older units, such as in the middle profile, 155,000 year old lava flow, which is clearly marked in the LiDAR and has about 14 meters of relief on a profile directly across it. The interesting part about this fault zone is it's very difficult to find lateral offset. For example, there's a suggestion of lateral offset right here on this margin of the flow, but when you go to this margin of the flow, it's more difficult to argue that there is a lateral component of offset. And yet there must be some lateral component because this fault system is nearly parallel to the velocity vector as indicated by geodesy. But again, these are very low slip rate faults. In Oregon, these are exciting. In California, they don't even catch the attention of anyone. When you approach the arc, the Sisters Fault Zone comes up in these black lines here and intersects the arc in this series of yellow lines over here, which is this region right here. Mount Jefferson is right here. And then there's a suggestion that faulting continues to the northwest on the into the forearc side of the Cascade Arc Range. And what's really cool about this, and it's just a classic LiDAR image where you could spend the rest of your life looking at this, is that these are very young post-glacial faults, definitely in the Holocene, because if you look at, for example, a place like this, here's a flow, lava flow, which came down into glacial topography, and both of which are cut by faults. And there are numerous examples of these. So these are not well known in terms of their age or offset, but the geological relations clearly indicate that they are post-glacial, which means in the Holocene. And thus that implies that in the north, the shear related to North American modern orogenic processes most likely crosses the arc in the region of Mount Jefferson. But as you go to the south, you have crustal extension in the Basin Range type geometry, which is partitioned between northwest trending oblique slip faults and north trending dip slip faults. And that structural style persists as you go to the north, but switches where north trending faults have oblique shear and the northeast trending faults have the dominant dip slip fault. So there's a broad zone here of separation between the forearc region and the back arc region, which defines the northwest corner of Basin Range. At a larger, perhaps more exportable set of conclusions, one of the implications of this is that there's a mass transfer occurring because of the location of the breakaway between the Basin Range province and the forearc, which is adding this piece of the arc and the back arc to the forearc block, which must now be moving with it and to the northwest. And the second piece here is that volcanoes such as Newberry and potentially the Mount Jefferson Cascade Arc volcano itself are located at structural complexities such as this transtensional stepover in the fault system, and thus the magmatism here on the northwest corner is intimately located and associated with faulting. If you look in cross-section then, let's see, yeah, if you look in cross-section then, if you're in the south, what the cross-section might look like is the Juan de Fuca plate coming underneath North American plate, the Oregon coast block, the forearc block, moving westward, northwestward with respect to the arc and the back arc and separating at the arc itself. But as you go to the north in the region at the northwest corner, you're most likely, in fact, adding a piece of what is the basement to the high Cascade Arc and a piece of the back arc to the Oregon coast block as a consequence of the structural ending and transition to shear along the plate margin. So you're all invited to come out and visit us anytime. This is a picture from the top of the Newberry volcano on a clear fall day. And you can see the Three Sisters, Mount Jefferson and Mount Hood arc volcanoes quite clearly. This is a caldera a lake forming in the core of the Newberry caldera. And of course, I have to credit all the people who actually did all the work, which is this big pile of collaborators and students. And thank you very much.
Thanks a lot, Andrew. You are slightly behind the time, but we have time for one quick question if there's one. Just type Q in the chat and then you'll get the word.
Okay. Should I stop sharing?
No, just leave it on. Maybe yeah. This relates to what you show. Otherwise, Gianretto, I think you have a question.
Yeah, I was wondering about what is controlling the strain distribution. Do you have inheritance in the, or a sort of a crustal template that is predating and that controls, or is it completely the present day stress field?
There are basically three contributors to the modern stress field, and the strain that you see. In terms of the strain, the older structure is most clearly indicated by the northeast trending faults, because those parallel the suture zone across which the forearc block was accreted to Western North America. But the region of the northwest corner of the Basin Range is also where there's an edge to the Juan de Fuca plate in the south. And so there's vertical axis flow in the mantle immediately below, which is directly contributing to the velocity field that you see at the surface. And then that's all being impacted, I think, by both the crustal thinning associated with Basin Range and the arc magmatism and the thermal signal associated with the corner of the down going subducting Juan de Fuca plate. So it's a fully three-dimensional problem that has to do with I think those three factors.
Excellent. Thanks again, Andrew. Then